lighting and that optimization. This is going to be fairly technical. I'm going to try to keep it pretty abstract and high level to start with. And if you want more specifics about anything I mentioned, feel free to grab me later. However, this is inherently a somewhat low-level thing, so I'm going to make a lot of assumptions about basic knowledge of graphics programming here. And I'll try to make as few of those as I can. All right, so first off, shader. Why do you care? What the heck is this? So this is light. This is what light does when it hits an object. The beam comes in and it bounces off in a bunch of different directions, and then some of it goes through at a different angle, comes out at yet a different angle, and may or may not scatter at a bunch of other angles. This is ridiculous. The equations for this are actually pretty well known, but they're way too complicated to actually do in any kind of reasonable speed on any hardware, ever. Even when you get into offline rendered movies, they do approximations of these. And they take hours per frame, where we have to do 60 frames in a second. So shaders are small programs that are run on the GPU that determine what happens for the pixels of your object when they are drawn. Most of the time, this is done to simulate one part or another of the interaction between light and that object. You could also use since you just have a general purpose program that you can run on your GPU, do other crazy things with it, including post-process effects, and very recently, just using your GPU to do more general purpose computing. This is outside the scope of Unity, but things like OpenCL and what's the other one?
Anyone?
CUDA?
CUDA, thank you. OpenCL and CUDA are both standards for running general purpose computations on your GPU, which is very nice for certain highly parallel problems. Outside the scope of this, however. Excuse me, it's horribly organized. Roughly what I'm going to talk about. Shader Lab. This is Unity's configuration format. This is the first entry point to shaders. I have to be very careful to draw a distinction between this and the shaders proper, however. Shader Lab is unique to Unity. Most of the rest of this is not. It is applicable to any engine you ever touch with different rules of setup. Surface shaders. These are another Unity-specific thing that generate a lot of the hard parts for you, rather the complicated, boring boilerplate parts, and let you hook into Unity's lighting system very easily. The lower level, we'll get into actual vertex and pixel shaders, the two types we care about in Unity. Again, more recent hardware supports other kinds that I'm not going to get into because Unity doesn't support them yet. And then I mentioned post-process effects and some other tricky things you can do with shaders outside of rendering individual objects. And I will probably avoid it unless people really want me to go into it. I have some very specific information about architecting your shaders for maintainability, if you are a shader programmer. So, Shader Lab. It's the Unity-specific configuration format. It determines what properties you can set on a material. It then breaks up into categories, subshaders, and passes. A category is just a configuration grouping of a bunch of subshaders. A subshader is one version of this shader for a particular hardware configuration. If you have a chain of subshaders, Unity will automatically determine which of those it can run, starting with the first one. And this is exceptionally useful because it means your high-end, super fancy bump mapped shader, well, if my hardware doesn't support this, I'll fall back to something simpler. I still don't support that, I'll fall back to something simpler. I'm on an iPhone. Okay, just put the texture there, forget about anything else. And then passes. Passes are the individual runs of shaders, and I'll get into a little more detail about them later because they're very important for draw calls and performance. Also within Shader Lab, you can configure fixed function shaders, which are the old way of doing GPU rendering, where the GPU itself just knows how to do lighting. You don't have any control over it. It's mostly irrelevant with any recent hardware, but Unity still supports it, and you can still sometimes do useful things with it. All right, passes. This comes back to the draw call problem. One pass is one draw call. What you do in a pass will vary. Unity can actually push a bunch of lighting information into one pass through various tricks, but ultimately one pass is one draw call. A shader that takes 3 passes to run is the same as drawing a 3-pass shader with a certain object. Is the same as just drawing 3 of those objects from a performance perspective. Exactly the same. So they're, as you can imagine, they're very important for performance. You're also, although you can use multiple passes on one object, you have limited ability to combine those passes. There's a set of blend modes that basically say, take the color that my pass produces and the color that was already there and combine them in this way. You can add them together, you can alpha blend them, you can make one 0 and just use the other one. And there's a few other options, but you don't have anywhere near the full flexibility you have in the rest of shader programming. Fixed function is, again, the old method of GPU rendering. Lighting information is calculated for every vertex. The results are interpolated just linearly between vertices across any given triangle. The mesh is exactly what you pass into Unity. Same UVs, same position, same color information. You have some ability to control texturing through the use of these set texture commands, which are a shader lab thing. I'm not going to attempt to give you the basic syntax of them. It's complicated. The docs are there. They're actually fairly good on this point. That lets you combine multiple textures in your fixed function shader in various ways. The only real reason to use these is that in some narrow circumstances, they're actually faster than programmable shaders. Mobile devices, and the older ones, older mobile devices, even the more recent mobile devices, there's no reason to do this anymore. Actually, their fixed function pipeline is faster than the programmable pipeline, which means that if all you want to do is splat a texture onto an object, which again, for a mobile device where lighting is expensive, this is typically all you want to do, you can use set texture to get very fast results and gain a few frames over attempting to do anything fancy. Surface shaders are a really cool fancy thing that Unity introduced in Unity 3.0. They allow you to configure, let's use a bad example. No, I'm sorry. They allow you to configure, oh wait, yes I do, I'm sorry. An example of this. Surface shaders let you configure a bunch of properties of the surface for lighting, and then just run it into Unity and it does the rest. Somewhat complicated example here, but I have some other stuff to do some fancy texture lookups, and I set my albedo, the color of the object, on lit, and my alpha. And that's it. This is all my shader code needs to do for a surface shader. The rest of that is junk for this specific example. Unity will then take that, integrate it fully with its lighting system, and just go. No boilerplates, no complicated configuration, does all that stuff for you. Advantages of this: it uses Unity's lights automatically and very efficiently. It uses shadows automatically. You can change the rules of lighting. You can use lighting that is wraps around an object generally, or is a toon shader rather than a normal smooth shading. And it will just work with the rest of it. And all you have to do is change that lighting function. It integrates with both forward and deferred rendering in Unity, without, again, you having to do anything fancy. These are all good. Bad side, of course, is that you have very little control and flexibility in this. You always use Unity's normal lighting environment. You don't really have any of those blend modes I mentioned earlier. And unfortunately, for anyone trying to learn how to do this stuff, it doesn't teach you anything. It hides most of the details of what the shaders are actually doing, and just leaves you in this sort of happy, magical land where everything is simple, for for better or worse. What is really going on in surface shaders, I will part the veil for you. Your one surface shader with the 10, 12 lines of code, whatever, generates a bunch of different variant passes for all of Unity's light types, for the shadow caster and collection passes to integrate with their shadow system, for both forward and deferred rendering, regardless of which you happen to turn on or off at a given moment. And this is, again, where passes and performance come back into it. By default, the first pass will draw your ambient light, 8 per vertex lights, spherical harmonics lighting, and 1 pixel light. This is actually quite a lot more than 1 light per pass, but everything other than that 1 pixel light is simplified. Vertex lights, lighting is calculated for the vertices and interpolated, as I described earlier. This is easy to see in most objects because it just looks kind of bad and it's really obvious where the triangle seams are. Spherical harmonics is goofy, and I don't want to go into the math because it's complicated, but it basically batches all the distant lights into your scene, regardless of how many there are, into this vague approximation that gets most of the detail, and only really fails when lights start getting close. Now the good news is, the transition between vertex and spherical harmonic and pixel lighting mostly is handled automatically. So we'll flag on Unity's lights, important, not important, rather, I believe always important, not important, let me decide. If you let Unity decide, it will take the most important light affecting any given object, and it does this per object, not per scene, so it's fairly smart about it, and do that per pixel. All the other lights, rather the next 8 less important lights, will be done per vertex, and everything else will be lumped into spherical harmonics. So this actually lets you get away with quite a lot very cheaply, because for anything other than close detail work, vertex lights and spherical harmonics lights are enough. Most of the time, if you're in an outdoor scene with, say, the sun shining down, the sun introduces 99% of your light. And if you have another directional light that is simulating some reflected light from the sky, and maybe the guy's carrying a torch, and there's a firefly buzzing around his head, well, yes, all those introduce light. But the amount they introduce is so much less than that introduced by the sun that the fact that they are being run in this less precise manner isn't actually noticeable. And again, if you let Unity just do its thing with this, you can then configure how many pixel lights it will use at most for any given object. Do this per quality setting, switch between quality settings based on your either user input or some automatic detection of how powerful the hardware is. Change the defaults depending on what device you're building for. Have your iOS version go to no pixel lights, while your desktop version goes to 5. You can use fancy GPUs. So after that first pass, where everything is complicated, it gets simple again. And it's 1 pass for every additional light. And now we're back into every additional light is an additional draw call. And things get bad again, depending on exactly what hardware you're on. But mostly you can get a lot of stuff into that first pass, so it's okay. The other thing that adds passes to this situation and can be a noticeable performance hit are shadows. You use Unity Pro and you turn real-time shadows on, things look nice, until you realize that you're adding an extra draw call per object per light. To do shadows, every light has to render information about every object it illuminates, and just to get the shadows that those objects are casting, and then actually render the objects it's illuminating, possibly modified by the shadows that other objects have cast. So shadows, especially if you have multiple lights casting shadows, can very quickly become a performance problem, and you should use them with care. Now, once you're out of happy surface shader land, we're also back into everything is clear what's going on land. In a Unity shader, you will insert CG program and NCG tags, within which you write your shader programs. A shader program consists, generally, of 2 functions, a vertex function, which runs for every vertex, and the results are then interpolated in between, and a fragment shader, which runs for every pixel, mostly, and takes as inputs the interpolated values from the vertex shader. And again, you can do all this per pass, so you can have a different program for each pass. I say per pixel mostly because the fragment shader actually will run for some pixels that aren't drawn. If those pixels then get discarded due to alpha cutoff, overdraw due to transparent objects and similar things, depth culling happens before the fragment shader, but after the vertex shader, so there you're safe. Most of the time, your shaders are going to be written in a language called CG. It literally is C for graphics. It was developed by NVIDIA. It is C-like. It has basic functions and a basic math library, and nothing else you're used to for more modern programming languages. It's not object-oriented. You don't really want it to be. Shaders are tiny, and they need to be tiny because GPUs are dumb. The vertex shader outputs a custom structure, just a struct, if you're at all familiar with C or C-like languages programming, which you can fill with basically whatever you want, and includes whatever texture lookup information you want, color information, other arbitrary values that you want to use for something fancy in your pixel shader. That information is interpolated by the GPU for all the pixels on a triangle in between the three vertices, passed to the pixel shader, which then actually outputs the color that gets drawn to the screen. CG is what you'll be using 99% of the time in Unity. There are two other shader languages, HLSL and GLSL, that are very, very similar in syntax, and you may be able to find more examples of them. However, they are platform specific. HLSL is DirectX only, it will only run on Windows. GLSL is OpenGL only. It will only run on the Mac and most mobile devices that which use OpenGL ES2. I don't know what WinPhone uses when it comes out. That may be an exception for mobile devices. That's not here. He would know. Things you can do with vertex shaders. Well, you can change the color. You can do rim lights. Lights that you modulate the color of the object based on the direction you're looking at it and the surface normal, and you can then have a light that just bleeds in around the edges of any curved surface. You can configure your textures procedurally. You can alter them based on slope or time or other parameters that you pass into the shader through the material. You can animate the vertices and distort them, again, procedurally, to do things like waving grass. The vertex shader also is relatively cheap as shaders go, frequently because there's not a lot to put in there, where the pixel shader is a little more congested. So if you can push things into the vertex shader, it's usually wonderful. It's basically free. Pixel shaders. Most of the time what you're going to use them for are fancy texturing solutions, either looking up your lighting value based on some strange combination of textures, using a ramp to create, say, a toon shader effect, using splat maps for something like Unity's terrain, where you have one texture controlling 4 others and that fade into various degrees. Alternately, bump maps, which are in a separate category because while they're still a fancy texturing trick, are the most common example of pixel shader usage. The bump map is just a texture that makes the normal look different per pixel, so that you can fake a great deal of detail with texture data rather than mesh data. And we get to post-process effects, also called full-screen image effects. These include color correction, bloom, or glow. They're the same thing, different names. Depth of field, which is just a more complicated one. All of them, under the hood, are a full-screen quad, 2 triangles, just filling the whole screen, drawn with any shader you happen to pass to them, so the full suite of crazy things. But one of the input textures is the original image that was rendered of your game. So for the case of color correction, You take your input image, you, in the pixel shader, take the color of it, look up into another texture that tells you what to change that color to, and output that. And now you have a color-corrected image. And you can do this in multiple passes to get more complicated effects or other things. And use again, the full suite of shader tricks available. This is all done through onRenderImage, which is one of the monobehavior events Unity exposes. Simply is called on scripts attached to a camera every frame with a texture parameter that is the original image. Yes?
When you're saying that the input of that post-processing effect is the image of the game, how is that available to you when you're writing a shader and you're configuring that input? How do you get a hold of that?
In onRenderImage, you'll configure a material, probably, well, yes, you'll configure a material. The material may be mostly configured by something you expose and let people configure in the Unity Inspector. But one of the things you'll do is, on that material, set its main texture to the texture that onRenderImage passed in, which is the original game image. And now in the shader, it's just available as the main texture.
What's onRenderImage? What's that?
That is a monobehavior script callback.
Oh, okay. Cool. Thank you.
A couple other shader plus script tricks that you can use to configure your shaders to do fancier things. Shader globals. These are one of my personal best friends in the world. A shader global is, there's a set of functions in Unity's shader class, shader.setGlobal blank, where blank is texture or vector or float or color. You set that value, and that value is now exposed to all your shaders unless it is overridden by the material. So if, for example, you want to have some lighting control texture you use to look up to do fancy gradient, excuse me, I shouldn't get too more complicated than I had before, tune lighting, where you have some kind of banded texture that says how quickly the lighting changes. You set that once in a shader global. All your shaders have it and don't need to think about it. You don't need to set it manually on all your materials. But you can set it manually if you want to override it for specific materials. Another useful one, shader LOD. Unity has this value set on all of their built-in shaders. It's just an integer. It ranges most of the time from about 100 to 600. And it is used as part of the subshader selection process. So normally Unity will just do this based on capability. Can the card run this at all? However, you can then tell, you can set a global maximum LOD, something lower, to something, really. So say 500. This means that any shader with LOD 600 won't actually run. Regardless of whether or not the card supports it, it'll just go back, try to find the next subshader. This is extremely useful for setting up more complicated performance fallbacks. I want my highest quality setting to have, the fanciest shaders. But I want my low quality setting still to require all the same hardware hard limitations, but be something that can run on, say, an integrated Intel card, which can do all those things but not very fast. So it's a simpler shader, but still Unity can't by default tell the difference. But I can say if I set my quality level to something lower, set the shader LOD lower, and now it will automatically fall back to the version of my shader with the lower LOD. Yeah, I can show an example of this a little clearer.
So very quickly, whilst you're going to show this example, does that mean that I can be very efficient? That you, or for a new player comes in from thinking about an onboarding, and I've got nanoseconds to capture your attention and lock you in. That like setting global max to 500 or lower means that I can have quite elegant, cheap detection of levels of hardware, and even if I'm like 5 to 1, you're on a high-end $3 rig to you want a Dell crappy.
It's related to that. It doesn't actually let you detect things any faster. This is all your manual control. However, given that you have some way to detect the quality levels, either by querying other parts of the system for the exact hardware you have, or user selection in graphics options screen. This lets you very elegantly control which of your shaders runs at any given time. So I'm sorry that this is tiny, but it's a little example over here. You have a category containing 3 subshaders. Each subshader has a little CG program block setting up some surface shader stuff. This one is LOD 600, this one is LOD 500, this one is LOD 250. In the game this is written for, 600 is the highest quality setting. So this is the fancy version. If we set to the next quality setting lower, it sets the global LOD to 500, and it'll use this one, which disables a couple features. This quality level is set even lower. Well, there's no other features to disable once I get past this one, so it's this LOD 251, which is the lowest this particular game will ever go. That is always used. All right. We'll stop and open to Q&A, because I just dumped a whole lot of information at you really fast, and I can go into more detail on any of it and probably take up the whole rest of the night by myself if you let me. So, questions?
I'm in. I have a few, but I know I've explained a lot, so if anyone has one, go first. Okay.
Go ahead.
Because I am, I don't know nothing. Toon lighting. What does that mean to me, like, I'm a creative? Why would I need toon lighting?
It's a choice of aesthetics.
So
you don't always want... Cell shading is
Okay.
the other frequent name for that effect, where you have hard divisions between degrees of shadow.
Not like literally like 1, 0, but like black 1.
Yes, like everything that is up to this point in the lighting is fully illuminated, and everything past that is 50% illuminated, say. Gives a cartoon-like effect with a single evenly illuminated area and another evenly illuminated darker area. There are various intermediate forms of that where you might have 3 or 4 bands, but it's the same principle. The reason you might want to do this depends entirely on the aesthetics you're going for in your game, but specifically for things like mobile development and other relatively low-end devices, you are not going to be able to make the most realistic game possible. People will expect your game to look like, PS3 high-end PC gaming realistic. It can't. The hardware won't support that. Sometimes, the better approach is to go for something stylized that you can get away with on lower-end hardware. And something like toon shading is a way to do that.
So my question to follow up, so doing something in toon shader will help to reduce the requirements on the hardware. Will it simplify the way
no.
you're printing it out?
It's not that toon shading itself does not simplify anything. However, rendering something that looks like a cartoon doesn't require as many lights or as highly detailed textures as rendering something that looks like, say, Battlefield 3.
But the process isn't the same in which that you can be like, okay, disregard all of the values between, my one band and my other band.
It's not actually any cheaper.
Right, okay.
I noticed it happens in a lot of shaders. How do you control pixels that are outside the shape, outside the polygon? Like, for example, the black line outside a toon shaded object.
If you want to have like a drawn outline around all
or anything, or like.
And so, was it Minecraft recently where there was not a model where they did like a very dramatic black line, cell shaded outline?
Not Minecraft. What has done that recently?
So
I don't know about recently. Okami did this to great effect.
It also you can use it
Wind Waker, the GameCube Zelda game. I'm sure there are more recent things. These are just the 2 I can think of off the top of my head.
And also actually for lights that wrap around an object but also glow around it.
Yes. To actually answer your question.
Sorry.
Anytime you want to break the edges of the polygon, you're in post-process image effects territory. There's no other way to do that. For the specific case of hard outlines, you can sometimes get away with it by drawing the same object slightly larger and just all black. That looks a little flaky from some angles, typically. The general purpose way to do that is to draw your unoutlined object, and then in a post-process image effect, look for the edges, usually based on looking up into the depth buffer, and draw only those pixels that are on the edge black. Similarly, if you're doing glow or bloom or any kind of color bleed thing, you render the unblurred version of the scene. And then in a post-process image effect, for every output pixel, look up into several input pixels that are scattered by some amount, and combine those values to produce the output value.
Are there any pieces of hardware that would struggle with that kind of...
iOS mobile devices, post-process are pretty much out.
Yeah.
This is probably true for other mobile devices as well, but I've definitely tried it with iOS, and it is not good. Doing any post-process effects requires using something called a render to texture, and that function in particular on iOS is just slow, ridiculously slow.
What's fast? What's fast?
Any desktop PC hardware?
No. We're all being told, like, tablets in the future, you know, like, how to make this work elegantly on iOS. What's good for iOS?
Not post-process effects.
No.
None. Don't
In terms
go
of
there.
what are good, what are any ones that we could fudge or approximate post-processing effects? And what is the biggest consequence of us not being able to have post-processing effects?
The most noticeable things you're going to lose are the ability to break the edges of polygons, which can take the form of glow, bloom, depth of field. Any of those effects where part of the scene gets blurry are out. You can get some of the related effects by controlling the output color on the per object shader. So you can have an object that like glows brightly and pulses or something, but that still won't break the edge of the polygons. You can sometimes get around those particular limitations by using particles and sprites. That runs into its own set of problems on iOS devices, transparency, as was discussed earlier, and even then it doesn't solve it in general. Most of the time you just have to deal with it, get around with it with either clever art or clever selection of your visual style.
When you talk about depth of field,